Good afternoon, everybody. Welcome back to the afternoon section. My name is Neil. I am currently a scientist in the Institute of High Performance Computing, Singapore, and concurrently a research fellow in the Complexity Institute of Nanyang Technological University. Today, it is my great pleasure and honor to chair a talk by one of the biggest names in mathematics within the last 100 years. Professor Gregory Chaitin, an Argentine-American mathematician, has made many important contributions to mathematics and computer science. And he has made many important contributions since a very young age. In 1966, at the age of 19, he published a very important paper that formed the foundation of what is now called Kolmogorov-Chaitin complexity, or algorithmic information theory. Another important contribution of Chaitin is his invention of the so-called omega number that is regarded as an oracle for Turing's famous halting problem. Professor Chaitin also has a long-time interest in philosophy in general and the philosophy of mathematics in particular. Interestingly, he believes that mathematics is in fact much closer to biology than it is to physics. In recent years, his attention is captured by Leibniz, the man and the philosopher whom he sees as a precursor of the idea of descriptional complexity. In opposition to Leibniz's principle of sufficient of reason, Chaitin believes that there are mathematical facts that are true for no reason. They are true by accident, and they are random mathematical facts. So without further ado, let us now welcome Professor Chaitin to share his insights into these very interesting subjects with a talk titled Leibniz on Complexity.
Thanks very much. Thanks very much. Hi, everybody. Now for something completely different. This morning you heard about the amazing capabilities of current hardware and software. So amazing that maybe we're a little afraid what is going to be left for human beings to do. So instead of praising amazing hardware and software, I would like to tell you about a remarkable human being, Leibniz, who's so remarkable that more than 300 years ago, he had a lot of the ideas which nowadays are the basis for this computer hardware and software technology that is so amazing that we heard about this morning. Okay, so Leibniz is a very remarkable thinker. He's a philosopher, mathematician, but he was interested in everything. You know, he believed in beyond boundaries. He would go from field to field, throwing out fundamental ideas. And I think the fact that ideas that when he threw them out more than 300 years ago, he died 300 years ago this year, 1716, this is 2016. I think the fact that ideas that sounded crazy when he threw them out more than 300 years ago are now really at the heart of a lot of computer hardware and software technology, and even at the heart of the idea of complexity, which is what I'm going to talk about today. So I would like to give you a feeling for this remarkable human being, and also to indicate that human beings are not obsolete. There are some remarkable human beings. When we're lucky, we can do great things still. So who was Leibniz? Well, Leibniz lived in Hanover, a small duchy in what is now Germany. He did spend several important formative years in Paris, however, where he learned mathematics from Christian Huygens, the great Dutch mathematical physicist, whose name I'm sure I mispronounced. Yeah, I'm sorry about that, but he's still a great mathematical physicist. So Leibniz is unusual that he learned mathematics late in life, but Let me tell you one thing that I think lawyers consider Leibniz a lawyer, diplomats consider him a diplomat. I'm a mathematician, so I consider Leibniz a philosopher. This is a statement that I found in a book in Vienna in French, and they didn't indicate the source, unfortunately. And some of the people at the Leibniz archive in Hanover expressed skepticism that this was actually said by Leibniz, but it could have been said by Leibniz, was the remark of a Leibniz scholar there. So Leibniz said, en français, bien sûr, without philosophy you cannot penetrate deeply into mathematics. Without mathematics you cannot penetrate deeply into philosophy. And without both you can't penetrate deeply into anything. So this is, I believe, the idea. Leibniz was an optimistic rationalist. Optimist is a word that Voltaire coined to mock Leibniz in his book Candide, or L'Optimisme is the subtitle. But it's a good word to apply to Leibniz because Leibniz believed that reason was capable of understanding everything, that we humans could understand the physical universe, we could understand biology even, and we could even understand God through reason. So he's a rationalist, and he's definitely an optimist as a rationalist. And I'd like to tell you a little more about him. First of all, I should tell you that it's not easy finding out information about Leibniz because Leibniz doesn't publish very much. The reason being that at that time there were no mathematics journals. To publish something you had to have permission of a king or some important noble. It was always dangerous because if you wrote something that could be interpreted as heretical, it would be very bad. So there was something called the Republic of Letters. And this was all the scholars in the deep thinkers in Europe would exchange letters with each other. This is how ideas propagated. And this was much safer than publishing something. For example, when you did publish something, it was often good to publish it under anonymously, under a false name. It was always a safe thing to do. So most of Leibniz's best ideas are found either in letters to the other intellectuals of the time, or else they were found in his posthumous papers. Leibniz didn't throw away anything. And when Leibniz died, interestingly enough, he left an enormous mass of notes, copies of letters, everything, ideas for his drawer. And this enormous mass of documents was preserved, fortunately, for a funny reason. The reason was that Leibniz had helped to make his duke, the last Duke of Hanover that he served, into the King of England, because England was without an heir to the throne. And Leibniz accumulated information by traveling all over Europe to show that the Duke of Hanover, his patron, was the closest relative, had the most claim to the throne. However, when the court of Hanover went with the Duke of Hanover to England, and the Duke became the king, Leibniz was abandoned, left behind in Hanover, because he had a mortal enemy in England, his vicious contemporary, the very famous physicist Isaac Newton. So he's a contemporary of Isaac Newton's, and he's much less well known than Newton, but I think in many ways he's fully as interesting and as remarkable as Newton was. So when Leibniz died, the King of England gave orders that all his papers should be seized and sealed in the royal archives, because among the beautiful mathematical and philosophical ideas that we admire were documents dealing with affairs of state, and these could not be allowed to fall into the wrong hands. So it was very fortunate that this happened, because it was only with the years after Leibniz's death that scholars poured through this enormous mass of copies of letters and notes that Leibniz wrote to himself in odd moments. He wrote, I don't know, maybe 10, 20 pages a day over his whole life. All of this survived in the Royal Archives. That people started pouring through these documents looking for treasures, and they found a great many. There is no definitive publication of Leibniz giving his his views on any subject. His views are constantly evolving, and as I said, he goes from field to field, like a butterfly throwing out fundamental ideas. He would always get to the heart of the matter and make suggestions which he rarely took the trouble to develop in detail, although the calculus is one case where he did develop the idea in detail. So this is giving you a sort of a picture of what the times were like. And let me now start going into Leibniz on complexity. Leibniz on complexity. Well, first, I think I want to tell you about Leibniz and the computer. Computing technology. Because this is more practical. At the time, it seemed completely ridiculous, but let me tell you about Leibniz and computing technology. The artificial intelligence project of the time was the AI project of the time was Pascal's adding machine. And this was at a time when most people couldn't read or write. So being able to do arithmetic was considered to be a very sophisticated thing, showing a great deal of intelligence. And what Leibniz did was came up with a mechanism that could multiply. So this was an AI breakthrough at the time, showing that machines could think. I don't know, at least they could reason, or at least they could calculate. And another thing that Leibniz is one of the creators of is the notion of mathematical logic, the idea that reasoning, if you had the right notation, could be like calculation, where the results of reasoning would be certain, because they would be as sure as 2 + 3 = 5. And this is the idea of mathematical logic, which Leibniz threw out some ideas on how to do, but again, he didn't work it through in detail. Now then there is Leibniz, dear to my heart, is Leibniz and binary arithmetic. So I talked about a calculating machine, very important. There is Leibniz and binary arithmetic. I would propose that a bit should be called, instead of a bit, it should be called a Leibniz. It's a unit of information. And I'll tell you why. As I said, Leibniz was interested in everything. And one of the things he was interested in was China. At that time, there was a Jesuit priest in Beijing trying to learn Chinese philosophy in an effort to see to what extent it was compatible with Catholicism, because they were interested in missionary work. And Leibniz was exchanging letters with this Jesuit. The Jesuits are the intellectual elite in the Catholic Church. They're brilliant men. And Leibniz was very interested in everything he could learn about China. And one of the things that the Jesuit priest, whose name escapes me, yes? Thank you very much. Pateo Ricci, yes. One of the things that he told Leibniz about was the I Ching as a method of forecasting the future, which are, I believe, it's 64 combinations, right, of 8 yes or no's. And Leibniz, having a great mind, immediately realized that you could do arithmetic just using zeros and ones. You didn't need to have 10 different digits. Just 2 possibilities would work. And he realized that you could do arithmetic very easily in binary, and addition and multiplication are very easy in binary. And he got very enthusiastic about this. He proposed to his patron, the Duke of Hanover, the third Duke of Hanover that he served, and who didn't much appreciate him, in spite of the fact that Leibniz helped to get him into the crown of England. He proposed to the Duke to cast a silver medal celebrating the discovery of binary arithmetic. And you can find among Leibniz's papers various designs, proposed designs for this medal. One of them is in German, another one is in Latin, and they show examples of addition and multiplication in binary, and they also have a few interesting remarks that seemed more mystical, which is that the one can create everything from nothing. this may be about binary arithmetic, right? 1 and 0. But the 1 can also be interpreted as God, and nothing means, 0 means nothing. So this was the idea that God can create everything from nothing. And then at the bottom, there's a reference to creation, if I'm not mistaken. So Leibniz is realizing, maybe I'm putting too much into this, but I think Leibniz realized that basically with zeros and ones you could create the universe, basically. You could represent anything with zeros and ones. And in fact, I believe there's a letter somewhere that I saw in a book where Leibniz is realizing that zeros and ones are arithmetic and zeros and ones are very easy to implement in physical objects, because you only have two possible states, something that every computer engineer knows to be the case. And there are letters which people have found where Leibniz is talking enthusiastically about the idea of having machines that can calculate and how useful this would be in human society and everything. He's trying to convince, I imagine, his patron to fund building his calculating machines, which, however, did not work, I'm sorry to report. But so these are some of the, and I remember Laplace commenting on Leibniz's enthusiasm for binary arithmetic. Laplace, after the French Revolution, commenting as an atheist on Leibniz's enthusiasm for zeros and ones, linking it to monotheistic theology. And I guess Laplace didn't get it, despite being a great mathematical physicist. So these ideas really seemed pretty crazy at the time. Now, 300 years after Leibniz is dead, we can look back and see that it's a remarkable anticipation of a lot of things. My friend Stephen Wolfram said that, some of us should go over and pore through the Leibniz archives looking to see if Leibniz comes up with the idea of a universal Turing machine. I don't think he does, actually, but it could always be discovered. Anyway, it's pretty tough to go through the Leibniz archives. His handwriting is difficult to read. He writes in Latin and French. His handwriting is pretty bad because he's writing fast. So you have to be someone who knows French from birth and who learned Latin very well, very young, to be able to figure it out. And just to add to the problem, the ink is finally, after 3 centuries, starting to fade. But I have spoken to people who used to transcribe the documents, a French lady, and she spoke to me very emotionally, saying that Leibniz thinks very clearly and he writes very clearly. He's a great mind. But when there were documents concerned with the charge of plagiarism that Newton's fans leveled at Leibniz, first of all, his writing starts getting very bad. He starts crossing things out and writing, and she even saw evidence of tears on the paper. So let me tell you a little bit about, this is a former British colony, so I don't know if I'm saying the wrong thing here. But you see, Leibniz published the calculus first, and the notation we use nowadays is Leibniz's. I think he went more deeply into the calculus. He was not as great a physicist as Newton. Newton, as a theoretical physicist and an experimental physicist, clearly was marvelous. But I think Leibniz was a better mathematician, a deeper mathematician and a deeper philosopher. And what happened was that Leibniz was the first person to publish the calculus. And then the Royal Society appointed a committee that was supposed to be objective to decide whether Leibniz had plagiarized Newton. And it's interesting that you can find in Newton's handwriting the very objective report that this objective committee wrote about the matter, where Newton is pondering exactly how strong he should make the text in his favor or not, So anyway, even great geniuses are human beings, is what this shows, I'm afraid. We all know that. So anyway, so it's a miracle that Leibniz's writings survived. But mostly he wrote for his drawer or in letters to people. And there is no definitive statement of his views. There is no book that summarizes his philosophy. And it's an enormous, massive text. And some of the important things we now regard important ideas of Leibniz were only discovered by scholars a century after Leibniz's death among his papers. And I'm going to be talking about his work on complexity, which was only discovered a century after Leibniz's death. So should I say something else about Leibniz before going on? And talking about Leibniz on complexity. Maybe I said enough about Leibniz and computer technology, hardware, software, binary arithmetic. So let's go on to Leibniz on complexity, in fact. So I know 4 texts where Leibniz talks about complexity. And the main one I learned from reading Hermann Weyl, by the way. Hermann Weyl is the person who discovered Leibniz's work on complexity. So let me write down Hermann Weyl. Hermann Weyl was a wonderful mathematician. He was also a mathematical physicist. He has 2 books on philosophy. And that's where he talks about Leibniz and complexity. So let me give you Weyl's version of these ideas of Leibniz on complexity, because I think they're in some ways clearer than the original version by Leibniz. So Weyl says that the notion of a law of physics actually is 2 notions. Law of physics, let me write this down. Law of physics really consists of 2 objects, a law of physics. On the one hand, you have a law. Well, you have an equation, say, which is the law. But on the other hand, you have to have a complexity measure, a notion of complexity. Why? Really, the notion of a law, the question of whether a physical system obeys a law or not, Hermann Weyl says, really requires a notion of complexity. Why? Because if you allow arbitrary, complicated laws, there's always a law, and the notion of law becomes vacuous. Okay, this is how Hermann Weyl puts it. Should I write that down? It's very important, but maybe I just repeat it. Okay, so here's Hermann Weyl version of an idea of Leibniz. The notion of a law of physics really requires a concept of complexity. It's a pair, it's a marriage, it's not just a single idea. Because if you allow arbitrarily complicated laws, there's always a law, and the notion of law becomes totally vacuous. Every physical system would obey a law. Any set of data would be lawful, you see. So you're not distinguishing systems which are random from systems which follow physical laws. So this is Weyl's version, but he attributes this to Leibniz. So let's see where Leibniz talks about this and what Leibniz says. So this is how I got to Leibniz, by the way, reading Hermann Weyl. So the text in Leibniz is called the Discours de Métaphysique. It's in French. Am I missing an accent here? I don't know. Discours de Métaphysique, Discourse on Metaphysics. Now, this is a document that was discovered a century after Leibniz's death among his papers, and it didn't have a title. The scholar who found it, who was editing Leibniz's papers, gave it the title Discours de Métaphysique. It's in French, so the title is in the same language as the text. One of the items in this relatively short document is, in fact, the idea of kinetic energy, which Leibniz was one of the originators of, and is not found in Newton's Principia, for example. And the idea of kinetic energy, the idea of energy is a very sophisticated concept in physics, and you can find, there was a beautiful book, I can't remember the author, talking about the development of this concept, and it's quite an interesting history. So Leibniz also did mathematical physics, but not at the level of Newton. And by the way, Huygens and Leibniz both thought that Newton's Principia was obviously ridiculous because of action at a distance. So it took years before, the same way that people thought that Darwin's theory of evolution was obviously wrong because it's based on randomness. You know, the nature is not intelligent, according to the original version at any rate. So, okay, so the Discours de Métaphysique, how does the Discours de Métaphysique talk about complexity? Well, it has, the place to look in the Discours de Métaphysique are what I think in French you call paragraphs 5 and 6. Maybe in English it would be called section 5 and 6. You know, I'm forgetting my French. So in those sections, Leibniz talks about what Leibniz tries to combine medieval theology with the new mechanistic philosophy which was the beginnings of modern science. This document, the Discours de Métaphysique, was written by Leibniz in 1686. That's the year before Newton's Principia. So modern science was very new at that time, and it was called the mechanical philosophy. And it was a legitimate question, is the world scientific? Can it be understood by physical laws? And Leibniz says yes, and he says why? Well, he says God has created the most perfect universe, which is one in which, on the one hand, the laws are very simple, and on the other hand, the phenomena determined by these laws are very rich and diverse. So this is a statement, in fact, of what it means to say the universe is comprehensible. The universe is comprehensible if it seems very complicated, but in fact, it's the product of very simple, powerful laws. Another way to put it is God is a great artist who uses the minimum elements to create this very rich, diverse world that we see here. So this is Leibniz saying that he believes the universe is comprehensible, that science is possible. It's an attribute of God that the world should be this way. But it's also a definition, if you're not interested in theology, of what it means to say that the world is comprehensible, that science is possible. Now, that part doesn't talk about complexity too much yet, although it's there. The idea that the laws have to be simpler than the data they explain. It has to be a compression. But it's clearer in paragraph 6. In paragraph 6, Leibniz says, well, he says, let's take a sheet of paper and let's take a quill pen, you know, those pens made of a feather, and you close your eyes and you just splatter the piece of paper with spots of ink. So you have a finite number of spots, points, on the sheet of paper. And Leibniz asks, well, what does it mean to say that these points presumably represent your measurements of the behavior of a physical system? And the question is, does this physical system obey a law or not? Or is its behavior random? And, well, Leibniz says, well, to say that there is a law would be to say that there's an equation which passes through those points, right? But, says Leibniz, there's a problem. He says, there's always an equation through any finite set of points. So the fact that there's an equation that passes through the data points doesn't enable you to distinguish a world where science is possible, which is lawful, from a world which is random or subject to the whims or caprices of, spirits. What does enable you to distinguish? Well, if the equation is simple, it has to be simple. It shouldn't be fort composé, which means very composed, I guess. There wasn't a word for complexity in French at the time. So when Leibniz talks about simplicity, he does use simplicité, but when he talks about complexity, he says fort composé, which means highly composed, which is pretty similar to the word complexity. Okay, so this is the idea that Hermann Weyl thought was such a deep idea, and Weyl discusses it in 2 books on the philosophy of science. The first book is called The Open World, 1932, and the second book is called Philosophy of Mathematics and Natural Science, 1949. But the best discussion of Leibniz's idea is in the smaller first book from 1932, which were 3 lectures that Weyl gave at Yale University in 1932, as a matter of fact. So that's how I learned that Leibniz was relevant to complexity. Okay, so what happens with this beautiful idea? Well, there's a problem with it, which is how exactly do you define the complexity of an equation? It sounds like a good idea in general terms, but mathematical notation varies as a function of time. Do I allow trigonometric functions? Do I allow Bessel functions? Do I allow hyperbolic trigonometric functions? So it seems a bit arbitrary how to measure the complexity of an equation. But if this is so fundamental for the philosophy of science, it would be good to have a rigorous, precise definition. And Weyl doesn't come up with such a definition. And Popper discusses this in a book which I think was published in English. I don't know German, so I never read the original German version. I don't know how it compares with the English version. But Popper has a beautiful book that my wife and I adore called The Logic of Scientific Discovery. And there's a chapter on this, on complexity of scientific discovery, 1959, the English version. There's a chapter on complexity in Popper's beautiful book, except that Popper unfortunately calls it, the chapter is called Simplicity, which now we would think is not the right choice. But anyway, and Popper basically mentions Weil and says if Weil couldn't come up with a precise definition of the complexity of a mathematical theory, this must be a hard problem. And that's basic. But Popper talks about the importance of the idea of simplicity in philosophy of science. Okay, so this takes us up to about 1959. How much time have I used here? I've used half an hour. Okay, so now I want to tell you what happens with these ideas. And it turns out there is a very simple way to take this idea of Leibniz's and Hermann Weil's and make it precise and get a mathematical theory about it. So these ideas come from about 1965. I like to call the field that deals with all this algorithmic information theory. There were three of us who sort of came up with the idea independently. I was the youngest of the three, which is why I'm the only one who's still alive. For how long, I don't know, I can't guarantee. But there was also Ray Solomonoff, who was pretty young too, but not as young as I was, and Andrei Kolmogorov, who to me seemed very old. He was my age, which doesn't seem so old anymore to me now. But so he was the first person to disappear, Kolmogorov. Now, the original version of our original motivation of the three of us was a little different in each case. Kolmogorov and I wanted a definition of randomness or lack of structure. So that was K plus C, define randomness, define lack of structure maybe is the best thing, lack of structure, lack of pattern. And Ray Solomonoff and I were interested in a toy model for what science is all about. For physics, toy model for science, for the scientific method. So let me tell you that toy model because I think this is the best way to begin. The real starting point of this theory is this toy model. But Kolmogorov, as far as I know, didn't need to start with this idea, but Ray Solomonoff and I did. These were three of us working independently. So what is this toy model of science? What is the scientific method about? What do physicists do? So the toy model, remember that Leibniz had a model where theories are equations, and the complexity of a theory is the size of the equation, roughly. Okay, so we have, in the original version, theory is an equation, and complexity is the size of the equation. Now, the basic idea of algorithmic information theory from a philosophical point of view is the idea of having a computer here, having experimental data you want to explain, and instead of using as your theory an equation, what you have is a program to calculate the data. So a theory is a program that you put in the computer, you run the computer, and the output is precisely your experimental data. This is this very simple model. You're not allowing noise, you're not allowing statistical theories. And notice that the experimental data in this is not points anymore on a plane. They're not real numbers. The experimental data here is a string of zeros and ones, and your theory is a program which is also a string of zeros and ones. And in this model, Leibniz's insight and Weil's insight that the theory has to be simpler than the data it explains, otherwise there's always a theory and it's meaningless. Here it is that the program that is your theory, which is your algorithm for calculating from the basic ideas of your physics theory, the behavior of this, the measured behavior of your physical system. The complexity of this is the size in bits, the complexity of your theory. And this has to be smaller than the number of bits of physical data that you're explaining. Because there's always a theory which is the same size. It just says, I measured this, you print it out, and so that doesn't count. That doesn't mean you understood anything. Doesn't mean that the physical system obeys a law. It could be lawless. So by the way, how do you define lawless? Well, the experimental data would be lawless. It would be unstructured. There would be no way to understand it if the smallest program is the same size as your data. That means there is no theory. The data is lawless, is unstructured, cannot be understood. This was what was of interest to Kolmogorov and to me, defining this an idea of lack of structure. So this comes as a payoff, as a corollary of this little model, toy model of what science is all about. Okay? And this is a very simple model that does not do justice to the real complexity of being a physicist, but it captures some of it. And what's nice from a mathematical point of view, since I'm a mathematician, not a physicist, is I can prove theorems about all of this. You can get a mathematical theory starting from this, and the theory is called algorithmic information theory. It has other names too. So that's the basic. This is recognizably Leibniz's idea. Leibniz says that if the Leibniz's idea and Weil's idea that here can be made precise very, very easily. So it's important that you have to do a concept migration here. You can't have your theories be equations and your experimental data be real numbers. What you have to do is you have to make everything discrete. You make everything into finite sequences of zeros and ones. Your experimental data is just a finite string of zeros and ones in this simple model. And your theory is too. It's a program. It's an algorithm to calculate precisely that, get as output precisely that experimental data. Okay? So then you just look at the size, the number of bits of explanation versus the number of bits you're explaining. And the smaller the number of bits of explanation, the better the theory. And if there is no explanation that is more compact or concise, then this is a lawless or structureless or patternless. There is no theory, no real theory. Okay, so this is Leibniz 300 years later, and it's Weil, 1932 to 1965, and not such a long time. Okay, so this is a simple idea, and I'd like to tell you a little bit what you can do with this idea, and it's stuff that I think Leibniz would have found very interesting, since he was very interested in mathematical logic and reason. In fact, I didn't mention that there were I found 3 more texts where Leibniz refers to complexity. The one that Hermann Weil found is the best, the Discours de Métaphysique, but there's a comment in the Monadology, which is a late work, Monadology, where Leibniz discusses what does it mean to prove something in mathematics. And he says the idea of a proof is that you take a statement which is complicated and you break it down, you analyze it as a consequence of simpler statements until you get to statements that are so simple that they don't require proof because they're self-evident. So here again he's talking about complexity. Another place that Leibniz discusses complexity, mentions complexity, which is sort of fun, is in a short document called Principles of Nature and Grace, where Leibniz says, he makes a remark that, I think I'm getting this wrong, the simplest possible universe would have nothing. No, I'm getting this wrong. You seem to be, are you a Leibniz scholar? No, okay, the remark is, why is there something rather than nothing? That's the question. He says this is an important question. Why? Because an empty universe is simpler than a universe which has anything in it. So you need an explanation for why there's something in the universe. And that explanation would be the laws of physics. I guess now we would say you're getting information coming in. Once you choose the equations of physics and the initial conditions for the universe, that generates a universe. So that, and if God makes this choice, that explains where it's coming from, or I don't know where that information comes from, but that explains why there's something rather than nothing. I think it's still a very interesting question. Why is there something rather than nothing? And then there's one last place where I never found the exact source. Leibniz seems to have been a rather nice person as a human being. Whereas I've heard nasty things about Spinoza, which surprises me. But Leibniz apparently once went to trouble to avoid stepping on a spider. And somebody asked, why did he take the trouble? And Leibniz said, well, it would be a shame to destroy such an intricate mechanism. So if you take intricate to mean complicated, this might mean that Leibniz recognized that biological organisms are very complicated. But I've never found the original source, so this is okay, so let's go back to, let me tell you what I think these ideas are good for. Basically, what they're good for is I would like to use these ideas, which come from Leibniz in a way. You can follow this chain of reasoning. And I would like to sort of examine Leibniz's rational optimism, that everything can be understood through reason, and see how it holds up, if we could criticize it. And you can use these ideas. This is a field called metamathematics. Metamath is a field where you use mathematical methods to criticize the power of mathematical methods. It's sort of a mathematical self-examination. And the basic idea in metamathematics is the idea that goes back to David Hilbert. It actually has a lot of people that can be credited with it, but maybe it was most clearly enunciated by David Hilbert. The idea of a formal axiomatic theory. Hilbert wanted one for all of mathematics, a universal, a single formal axiomatic theory for all of mathematics. So there is this notion of a formal axiomatic theory which has a finite number of axioms. It has an artificial grammar. You use mathematical logic. And this is sort of like a machine, because in principle, you can systematically start deducing all the consequences of the axioms applying the rules of logic. So in theory, if you were very, very patient, you would eventually totally mechanically get every possible theorem. But this idea is important, according to Hilbert, because Hilbert believed that mathematics gave absolute truth. And according to Hilbert, what this meant is that there should exist a formal axiomatic theory that would be completely mechanical. You wouldn't actually use it mechanically, but in principle, in theory, the idea that it's totally rigorous, that it's objective, that it's black or white, there's no subjectivity in seeing whether a proof is correct or not, means that there ought to be a sort of a machine that would automatically produce all the consequences of the axioms. Okay, so this is the idea of a formal axiomatic theory, which is an important idea. And using this notion of complexity that I just talked about, which is really the size in bits of the smallest program for something. This is a program size complexity is really the idea I'm using here. I should write that down. Program size complexity. There are many flavors of complexity for different applications, right? This is the kind of complexity that is most useful, in my opinion, in metamathematics. It may not be at all useful in the real world, unfortunately. I know most of you are concerned with the real world, but I'm more concerned with this kind of stuff. So let's apply this idea of program size complexity, where we measure the complexity of something by the size in bits of a program. So you can apply this to a formal axiomatic mathematical theory, and then you get a measure of the complexity of that formal axiomatic theory. And it's measured in bits of information, of algorithmic information. It's actually the size in bits of the smallest program that systematically applies the rules of logic to the axioms and generates every possible theorem. It's an infinite computation. Okay, so it's the size in bits of the smallest program that does that. That's a technical fact, but you don't need to know that. So the idea is that there's some way of measuring the complexity, the amount of information in a mathematical theory, if it's a completely formal mathematical theory with no subjectivity, with everything specified precisely. Okay, so you can measure the complexity, and it's measured in bits. You get a finite number of bits. And you can also apply this measure to the Platonic world of mathematical truth, of pure mathematics, and ask, what is the complexity of this Platonic world of ideas, of all mathematical truths? And it turns out that, you can apply this complexity measure, it turns out that the complexity of the Platonic world of all mathematical truths turns out to be infinite number of bits of information, of algorithmic information. But your complexity of any mathematical theory is only a finite number of bits. So this means that any mathematical theory can only capture an infinitesimal part of the whole truth, because the whole truth has an infinite complexity, and our theories only have finite complexity since we're finite beings, right? So this is the reason that you were kind enough to mention my provocative remark that pure math is really, in some ways, a lot like biology. Biology is famous, theoretical physics is famous for the idea that the basic equations are simple, right? You could put them on a t-shirt. That's supposedly the idea, right? There's no point in doing theoretical physics if the fundamental laws don't fit on a t-shirt that you can sell to undergraduates. But biology, we know, isn't that way. Biology is very rich. There are no general laws. There are always exceptions. It's a lot of information to specify a biological organism. There's no simple equation for an elephant or a horse or a human being, right? So in a sense, pure mathematics is even more biological than biology, because biology is very, very complicated compared to theoretical physics. But it's only finite complexity, presumably, whereas pure math is infinitely complicated. So in that sense, it's more biological than biology itself. Shouldn't take that too seriously. It's just intended as a provocative remark to annoy mathematicians. I hope there aren't any mathematicians present here. My talks are really intended more for physicists than for mathematicians or computer scientists, as you can probably tell. Okay, so that's one application of these ideas. So this is a kind of a general incompleteness result. Okay, so we have any theory has finite complexity. All of mathematical truth has infinite complexity, okay? Exclamation mark, exclamation makes. This is a sort of a complexity version of a famous result of 1931 of Kurt Gödel, but the reasoning is completely different. This has a very different flavor. It deals with information and complexity, which Gödel doesn't discuss. Now, there is one last area of application of these ideas that is sort of tentative, and that's to a theoretical biology. Remember that I started off this talk, that's what I've been doing since I married Virginia. Besides being my muse, she's inspired me, but also we've worked together on this subject, which is an attempt to look at a biological theory or a biological meta-theory. Remember this remark of, this very optimistic remark of Leibniz? Well, if you take this seriously and you look at biology, and then there ought to be a mathematical theory of biology, a theoretical biology. Leibniz already could see the beginnings of a theoretical physics, and he has in some place a very optimistic remark that maybe with the centuries, human understanding and mathematical ability will reach the point where we can even understand the complicated equations that deal with living organisms. Okay, he says that, I think, in some place in a letter, very optimistically. Now, if you look at current biology, it is not like, there is no theoretical biology that is like theoretical physics. Theoretical physics is really very close to physics, right? Physics really is very mathematical, in its essence. And it's simple mathematics, even though calculating the consequences can be difficult. The basic equations are remarkably simple in theoretical physics. But biology is not that way at all. So does that mean that Leibniz's rational optimism has failed in the field of biology? I would hate to admit that my hero could make such a grievous mistake. Optimism is a good attitude to have in life. What can one do with biology? So I've, in the past few years, this is rather tentative new work, working together with Virginia and with a student of mine in Rio de Janeiro called Felipe Abraham. We've been working along the following idea that I just want to describe to you. The idea goes like this. Biology doesn't really look like theoretical physics. There would be a theoretical biology that is as close to biology as theoretical physics is to physics. That doesn't look possible, right? So what is possible? Well, I think that theoretical biology has to be a little further removed from biology than theoretical physics is from physics. And here's my suggestion. seen from a vast distance, I don't know too much about biology. I think it's a fascinating subject. But seen from a vast distance, I noticed that DNA is a little bit like a computer program, right? So in a way, what biology is about, the theory of evolution is the fundamental theory of biology, right? Darwin's theory of evolution. So what biology seems to be about is about what happens when you make random mutations on DNA and apply natural selection to that, and you see what happens. So my suggestion is, instead of making random mutations on DNA, let's make random mutations on a computer programming language, on computer software, and see what happens. So the idea can be described as looking at the evolution of mutating software, or considering life as evolving software. And the sort of idea is, instead of looking at DNA, which is, I think, in some ways a digital algorithmic language, but it's one that we don't fully know, and it's very complicated, let's look instead at the effect of mutations and selection applied to programs in a computer programming language that we've designed, that we know exactly how it works. So that's the proposal to do. I've optimistically called this metabiology, but it's just a proposal for a possible research direction. Virginia, my wife Virginia, now he's an ex-student, he already got his doctorate with me with a very nice thesis, Philippe Abraham, and I have taken a few baby steps in this direction that are encouraging, but it's just a little toy theory in a way. I talked about a toy model of what scientists does, right? And I talked about what a formal axiomatic theory is. It's a program to calculate the theorems. And now I'm saying, well, let's throw away the bodies and think of organisms just as computer software. And let's make random mutations on the computer programs and apply selection and see if evolution takes place. So these are organisms without bodies. They're only organisms, they're software organisms that only have DNA, but I'm using a computer programming language instead of DNA. And can we make a mathematical theory? And the answer is you can prove some theorems. It does look encouraging, the first steps. So what I guess I'm trying to say is I don't think that Leibniz's optimism is incorrect in biology. I just think that biology is different from theoretical physics, and maybe this indirect approach is the best you can do if you want to prove theorems. The theorem I'd like to prove, of course, is that evolution works and explains all the diversity of organisms you see here. That would be the basic theorem that one would try to prove with a theoretical biology, I think. So that's my suggestion there. So let me just compare these three toy models. One toy model is science. As a computer program goes in and calculates the experimental data, everything is zeros and ones. It's bits. The theory is bits. The data is bits. That no quantum mechanics, no noise, no statistical theories. You have to calculate bit for bit the data, right? Okay, so and you're not interested in prediction. You're only interested in understanding. You already have the data. So this is a very limited view, toy model of physics. Then there is the idea of a formal axiomatic theory, which is also a toy model of what mathematicians really do. This idea that you can mechanically calculate all the consequences of the finite set of axioms using the rules of logic. This is not how mathematicians actually work. However, mathematicians have made a religion or a fetish of this toy model. They actually believe that it reflects the essence of mathematics, and this is due to Hilbert's influence, I think. But I think they're wrong, but you can't tamper with people's religion, okay? So now, and then I'm proposing this equally simplistic model of what biology is all about and what evolution is all about. And there it's very obvious that it's very limited compared with real biology and real evolution. And I think actually all three models are toy models. The reason you make these very simplified models is that to be able to prove mathematical theorems, you have to do that. Mathematics cannot deal with messy, complicated situations very well. In that case, you have to do a computer simulation. Don't try to prove theorems. Okay, so since I want to prove theorems, I have to use these toy models. But I admit they're limited. And the most limited one of all is this toy model of biology that I just mentioned to you. But I think that in the context of the other two toy models and this whole system of ideas, which can be traced back through Weil to Leibniz, that maybe this model looks a little bit more persuasive than it would if you just, encountered it on a, on a dark alley one day when walking through Singapore. You'd say this theory, this toy model of biology is ridiculous. But if you put it in this context, this whole system of ideas, I think it maybe looks a little bit more persuasive, or at least persuasive to the point where maybe you might think it's worth pursuing to see if you can flesh it out into a theory with a little more substance. For now, we can prove a few theorems, which is very encouraging. When you set up a definition in a mathematical theory, the real test is if you can get a sort of a clean proof of some nice result. If you can't, it means that the concepts are not workable mathematically, and you've got to switch the definitions. And the first test is that this sort of toy model of biology, you can actually prove theorems, which is encouraging. But I don't know how far you can get with these ideas. Okay, so that's the story I wanted to tell you, and now I think I went a little over my time even. I'd be happy to try to answer questions, or you can throw rotten tomatoes or whatever it is. Thank you very much.
Thanks, Professor Chaitin, for a very stimulating talk. So the floor is now open for questions.
Thanks. Great. I love the story about the EG and his Leibniz's point about being able to create. What was it? Create the universe out of zeros and ones. Was that the line?
Isn't that terrific?
I love that. So I'm asking.
Yeah, Leibniz is terrific.
I mean, so here's my question to you, and it's maybe an unfair question because I'm
For 300 years, nobody got it, and now it's obvious to us. Finally,
Yeah, that's cool. It's amazing.
Yeah,
so
yeah.
here's my question to you. I'm asking you to kind of get into the mind of Leibniz, if that's possible. But do you think, was he thinking by that statement of a kind of a simulation that we think of in like abstract models? Or do you think he was thinking of like the mind of God and that kind of a view?
Well, I think he was thinking of all of those things simultaneously. That's a good question. Leibniz was aware of calculations and algorithms, right? He was aware of symbolic systems. He realized that zeros and ones could basically represent anything. That's very clear, right? He was aware of the power of having machines do computation, So it's really quite fascinating to see all these ideas. Now, he doesn't go all the way to define a universal Turing machine and do Turing's 1936 paper. No, we haven't found yet. I don't know if it's there. There's still thousands and thousands of pages of fading. Wolfram thinks that maybe. Stephen Wolfram thinks that maybe Leibniz came up with this idea. But you can see lots of related ideas all floating around, So he clearly has a remarkable mind. But sometimes you have to wait centuries to realize that an idea that Leibniz threw out has some content. Laplace is mocking this idea of Leibniz's, of everything coming from zeros and ones as being, a monument to monotheistic theology or something, you see. So, whereas we think it really expresses the essence of current computer technology, or at least part of the essence, See, he's really a remarkable guy. Now, it's possible that we're imagining all of this. People like to create heroes, right? So, but I think, in all fairness to Leibniz, he is a very deep thinker, and he does throw out remarkable ideas that really people didn't appreciate for a while. The part of the reason that his contemporaries couldn't understand it is, first of all, he didn't publish most of this. Most of it was for his drawer. Some of it were letters that he circulated. The other problem was that he was interested in everything. He really took seriously this beyond boundaries parallelism. He was interested in everything. So he would go like a butterfly from field to field and throwing out fundamental ideas that he rarely paused to develop in detail. So the calculus is one case where he did develop it in detail. And by the way, Christian Huygens, I'll never do justice. He didn't like the calculus because the idea was that the calculus made mathematics mechanical. You just take the formalism of differential calculus or something, And any fool can automatically, following a few rules, get to the answer. And Christian H. Preferred proofs where in each case you would get the reason that that particular result made sense. You know, a general method that you apply sort of mindlessly, to him was debasing the beauty of mathematics. But we don't think it was debasing the beauty of mathematics, because we recognize this idea of mechanically doing things as the basis for the idea of the computer, you see, as being a very deep idea. So even a great man, the man who taught Leibniz mathematics, didn't get it. You know, didn't get this idea of Leibniz's, which now resonates with us very well. So the question is, are there other ideas in Leibniz that only 100 years from now people will realize was a good idea? I don't know, but it's possible. But I think they better hurry and scan all those pages before they fade completely. Another question, maybe?
Yeah. Of course, I enjoyed your talk, as usual.
Hi,
let me add something to your discussion about Leibniz. I don't know whether we have come across or not, but somewhere he has this passage about what he calls divine machines. Now, these are the living systems, and he has, by deduction, this idea that in contrast to the everyday mechanics that we know, somehow they seem to be, as he puts it, infinitely divisible, right? So you cut it in half, and then there is still something like, you know, it can still metabolize forever. So there is a machine-like behavior even if you go down. And it's very clear that he figures out somehow what an enzyme must be, right?
Really?
I mean, it doesn't say molecule, but that would be for us, you know, the ultimate conclusion. There must be an invisible machine, or rather a set of invisible machines doing some work. So that's another brilliant foresight of him I wanted to add. But I also have a question, if I am allowed to ask.
So these are human machines and divine machines. Human machines are
exactly.
normal machines. Divine machines are biological organisms.
Exactly.
Because if you break a human machine in parts, the parts don't work anymore. But if you break one of the parts are still alive.
If you take a sponge, you know, if you take a sponge and you press it through a filter, right, you know, the individual cells will, and of course, if you wait enough time, the sponge is actually going to reaggregate. It will have a different macroscopic form, but because of the cell adhesion molecules, it will reaggregate. So, I mean, he must have similar things in his mind, which I think is brilliant. Now comes the question. The question is the following. Do you think that metabiology is to biology as metaphysics is to physics?
But I like metaphysics.
Okay, but that's the question.
Remember, the paper by Leibniz that I refer to is called the Discours de Métaphysique. So for me, metaphysics is not a dirty word. It's true that...
No, I'm just asking. No, I didn't say it was dirty. The question is whether...
Well, I don't know to what extent. Look, that's a good question. You know, the Discourse on Metaphysics is this document by Leibniz. It's not the name he gave. Then the stuff on incompleteness is called metamathematics already. So I don't know why I thought, I can't fully justify it rationally, I thought this approach to biology maybe should be called metabiology. I don't know, maybe it's goofy. I'm not sure that makes sense. Well, my wife Virginia has analyzed this, and she claims it makes sense, that it's really a meta theory, that it's not a theory. What I capture are, what is it, basic principles. It's not really a theory of biology. It's a theory that captures some basic principles. I don't know, Virginia's giving a... Please say that. What is it? Okay, it captures... Say it, please. Okay, it captures basic principles that rule the phenomena, not the phenomena themselves. So in her opinion, she's the epistemologist in the family. Virginia thinks that it is a meta theory.
But it's not. It's not as metaphysics is
Yeah.
Yeah.
Hi,
Well,
Vernon.
hi. Great, thank you. I've two related questions, and they're out of a couple of your popular books, Metamath, and the other one on Darwinism?
Proving Darwin?
Proving Darwin. Yeah. Anyway.
Which the book doesn't do, by the way, but the publisher wanted a title that would sell.
Okay.
It didn't sell anyway.
You make a couple of statements towards the end. They're just almost like aphorisms. And I'm wondering if I could get you to say more about them. One is that if you think about a computer or the computer, we tend to think of that as a piece of hardware, and it morphs, it gets more complicated. But it's definitely a machine, a piece of hardware, and we've heard a lot of consequences earlier today about it. But you have this statement that I'd love you to say more about, and that is the computer is a powerful new mathematical concept. The computer is a concept. Moreover, it's a mathematical concept. Say, like an integral would be, or a topological space. The second thing is that so one of those two books, you also say that mathematics itself is changing, and it's becoming less continuous, less, I think, something like less Newtonian. I forget, there's two or three other adjectives, and more discrete, more algorithmic.
More Leibnizian.
Yeah, and more organic, if I remember. So if you can say anything about
Sure.
either of those.
Oh, but yeah, I'll be happy to do it. By the way, I wish Sidney Brenner had been here. If he had, he was inspired to go, I believe, I would love to check this with him, his autobiography says he was inspired to go and join Watson and Crick at Cambridge, he was in South Africa, by reading von Neumann's beautiful paper, The General Logical Theory of Automata. And I tell that story as best maybe I'm fantasizing as best I can unravel it in the book Proving Darwin. And that gives more substance to metabiology. Metabiology is really attempting to go one little epsilon, one little step further than that original paper of von Neumann's. The same way that Leibniz talks about human machines and divine machines, von Neumann talks about artificial automata and natural automata. An artificial automata is a computer, and a natural automata is a biological organism. So that's analogous. So anyway. Oh, now going back to your question. Yeah, you know, the computer is absolutely revolutionary as technology, right? We were talking about that this morning. The two talks this morning are, you know, quite a punch in the stomach, right? So, but I like to be provocative to wake people up. And I think the computer actually is more revolutionary as a philosophical concept than it is as a technology. And it's tremendously revolutionary as a technology. And, you know, Doug Robertson was referring this morning to that idea that, you know, now we do experiments in silicio. The math in the computer is actually always discrete, really. It's a different kind of mathematics. You're more interested in simulations than you're interested in proving theorems. I still would like to prove theorems, but I can only do that by working in toy worlds. If you're dealing with the complexity of reality, then you're more likely to want to do computer simulations in silicio experiments than to prove theorems, because you can't prove theorems about anything that's messy and complicated, but you can do very good simulations of the behavior, say, of traffic flow in Singapore, for example, which I would never try to prove theorems about, right? So yeah, I'm being provocative. I think the computer is well, I don't know what you think, Virginia. I think it's a revolutionary idea in philosophy. I have a paper called Epistemology as Information Theory. I think Doug Robertson was referring to that too. But, you know, this is just my personal point of view. I'm enthusiastic about all this. It's natural. This is what I spent my life on. I should have met Virginia earlier. I would have spent my life on other things. So, but the philosophical community has been friendly. They've been nice enough to invite me, sometimes to give talks. But I wouldn't say that everybody has dropped everything they've been doing in philosophy to turn to this new viewpoint. But it is a new version of philosophy which is closer to computer technology and computer theory, which is the big paradigm change, it's the big tsunami tidal wave of our time. So I think this kind of computerized version of philosophy, its time will come. It's happening. Because you need a philosophy to accompany a computerized world. And so what is one version of this? Digital physics. People like Ed Fredkin or Stephen Wolfram, who like to think of the world as a giant computer, and wonder, or Gerd Tuft, I think, has some of these ideas too, although I missed being at a meeting with him in the Netherlands. So this is the idea of, can you think of the world as a computer and that it's actually discrete? Is this fertile in theoretical physics? Up to now, I would say it's not too fertile, but it's intriguing enough for a real physicist like Gerd Tuft to look at it a little bit. And Stephen Wolfram, at least, is a real physicist too. Ed Fredkin is a... Well, math is changing because there's much more emphasis on algorithms, on constructive proofs. The traditional way to prove that something exists, like the solution to a partial differential equation, is assume there is no solution and derive a contradiction. That can be very elegant. Constructive proofs tend to be more complicated than a proof by contradiction. But with algorithms being so important and the computer being so important, now people are much more tending to do constructive proofs. And and discrete mathematics has really flourished because of the computer also. So the whole thing is marching in step. It's not just that computer technology is changing our lives because we have these wonderful cell phones. It actually does change the way you do mathematics, some of the emphasis. I mean, some pure mathematicians will keep doing this very theoretical stuff that Doug Robertson referred to at the end of his talk. Nobody's going to... that's a very strong tradition that I don't think will die out. But it's not all of mathematics. And mathematics is changing, and there are new versions of philosophy, of philosophical ideas that are tied in with the notion of algorithm as a basic philosophical concept. So who knows how far this will go? There may actually be a digital physics, or there may not. Whether it's fertile to look at the world as a giant computation. Well, you already have quantum information theory. And quantum information says that the world isn't built out of classical information. There's not Leibniz's zeros and ones. It's built out of qubits. But it does talk about information and building the world out of information and computation, except that they're quantum versions, not classical versions. So that's a place where physics has been reworked, a very fertile reworking. I think it's fair to say that this new version of quantum mechanics is really still 1924 quantum mechanics. But it looks very different when you describe it in terms of qubits and computation. They think of physical systems as computing on qubits. And this is a very fertile approach, theoretically, not to mention the technological implications. So that's already a step in combining the notion of information and computation with physics. Although the people who tend to talk most about digital physics, like Ed Fredkin or Stephen Wolfram, really seem to be thinking more in classical physics terms, certainly than quantum physics. Certainly the stuff I'm doing is all classical computing, it's not quantum computing. Did I answer? Okay, it's a pleasure.
I was just having a question about, coming back to your biology as software. So I remember this book from Darcy Thompson on growth and form in 1917.
Beautiful book.
It's just amazing. And for me, that would be like a starting point when we try to describe biological processes as a set of transformations from one space to another space. And so
here it's software space. In his case, they were geometrical spaces.
But to some extent it's the same. And so it's basically like an information processing. So I was just wondering, do we need something like a Turing kind of information theory on the emergence of properties that you find in biology?
Well, this model of biology is embryonic. What I have a good analysis of is the notion of a mutation. according to this theory, a mutation is an algorithmic mutation. You know, normal mutations in molecular biology are what? They're point mutations. You change one base in place, or else they're indels. You either insert a base or you delete a base, right? So I couldn't get a nice mathematical theory using this. Instead, what I was forced to use was a notion called an algorithmic mutation, which is sort of a global thing. An algorithmic mutation is a program that takes as input an organism and produces as output a new organism. So it can be any program. The organism is software, right? My organism is a software organism, so it's a string of bits. And the mutation is also software. But and then you can talk about the probability of a mutation in terms of the number of bits in the program. You know, there's a natural measure on the space of all possible mutations of how probable they are. The simplest mutations are the most probable, and very complicated mutations are much less probable because they require more information. And this is sort of a natural analysis of the notion of mutation, but it's a more complicated notion of mutation than is normally in molecular biology. But I couldn't really get a decent mathematical theory with proving theorems with stuff closer to real biology. And I found that by allowing algorithmic mutations, all of a sudden everything fell into place. Now, I don't know if their viruses maybe are a little bit like algorithmic mutations. I don't know. I don't know if nature uses this idea. Ursh, you could come in maybe.
Well, that's a very technical question, but there are other types of changes, for example, due to transposition events, that can come rather close to this kind of thing. And then you would even have a distribution, you know, with the usual point mutations, and then, you know, something like the transpositions, and then you have whole genome duplications and so on. So I'm not saying that this is very too far. Of course, the mapping is not complete at the moment. I wonder if I am allowed to ask another question. I don't want.
Can I make a comment first before you ask the question? Okay, as a pure mathematician, I am not trying to capture all the details of real biology because it's a lost cause if I want to prove theorems. So I am happy if I have something that is like biology, you know? So I try to capture some of the features, and the question is which are the features to capture? For example, I don't include bodies. If metabolism and bodies are your thing, then my theory is useless for you. My organisms are just DNA. Basically, they're just software, right? So, you know, this is what you have to do in order to develop a mathematical theory. And then after you've done it, if you can prove some theorems as a mathematician, you feel a little better. You know, there's a big sigh of relief. But then comes the sad moment of saying, is this relevant to the area that inspired this theory, which is real biology? And I don't know. Virginia raised that question right away. She said, when I was feeling unhappy about algorithmic mutations, Virginia said, well, when concepts migrate between different fields, one of the important things is take the concept back to the field where it came from and see if it's relevant. So she said we should look at biology and see if there's anything like an algorithmic mutation. Whereas I was just bemoaning the fact that I was using algorithmic mutations. I didn't have the courage to think that there might be something like that in biology or not. So you had another question.
Okay, so the question is the following. Well, it's rather deep, so may not get a short answer. But the question
I won't be able to answer it at all if it's a deep question.
The question is that some other people have also asked, as you know, whether biological evolution is algorithmic or not.
Ah, your talk is on that, I noticed, yeah. Rather than random, you mean?
No, in the following sense. And take the argument of Stu Kaufman, for example. His argument is that, unfortunately, you cannot pre-state all possible pre-adaptations, you know, of an organismic lineage, right? Just as you cannot pre-state all the possible uses of a screwdriver. There will be obvious uses, but there can be somebody in the audience to come up with something again and again and again, and you don't know where it ends, whether it's finite or infinite or so.
Right.
And this opportunistic nature,
this open-endedness.
Exactly. If that's a crucial element, maybe because of the nature how matter, physical matter, is constructed, then you could say that although evolution has a very important algorithmic part, but in toto, it's not algorithmic.
Yeah, I think that's a very deep insight of Stewart's, and the issue you raise is a very deep one. I can tell you in this little toy model, I have a space of all possible organisms, which is the space of all possible programs. This may be very unrealistic. It violates the principle of open-endedness that you've been discussing. So that could be a big limitation on the theory. So what my view of evolution is that it's a hill-climbing random walk on software space, because my organisms are just software, and it's hill climbing. It's a random walk because I have random mutations, and the hill climbing part is that the fitness has to increase. And I didn't talk about how you. So for me as a mathematician, it's nice to have a space over which I'm working, and I pick the space of all possible algorithms in a universal programming language. Now, so that sort of sidesteps the issue that you and Stewart were discussing, which I think is a very deep issue, which just means that maybe this model doesn't reflect some of the fundamental aspects of creativity in the biological domain. I think it's an important question to think about.
Great, thank you for the lovely talk. So I guess my question comes along about sort of non-computability and algorithmic information theory. So as you mentioned, alluded to, so we can find all these mathematical axioms, and the amount of algorithmic information they must contain is finite. And at the same time, we know that the amount of information that all mathematical truths contains is infinite. And now in the physics community, we sort of find similar things, where the number of different ways of physical truths about physical systems is much greater than the amount of axioms that we could possibly ever write in physical laws.
Are you a physicist, by the way?
That's a difficult question to answer, but partly, yes.
Okay.
So I'm a quantum information theorist. So
okay.
People classify me as either a physicist, computer scientist, or something else entirely.
Okay.
Okay, so, so my question is, I'm very curious about this map to biological systems, because I guess I think very similarly. I think about DNA as information and biological organisms as programs.
Yeah, so, this is not, I'm not claiming that this is by any means my idea.
Absolutely.
This is an idea that's in the culture, right? It's in the air. But I'm trying to see if that's enough to make a mathematical theory, taking that as my starting point.
Absolutely. So I'm curious in terms of, one of the things that I'm very much interested in is how does this sort of algorithmic information, I imagine it can be generated through this evolutionary programming procedure, because as we know, using genetic programming, we've developed a lot of very interesting programs. But is it possible to prove something about that once such an evolutionary program runs for a sufficient amount of time, that there will be generate sufficient complexity so that there will be truth questions about the population that cannot be answered from the axioms that define the programs to begin with? So something where spontaneously non-computable problems are generated.
Yeah, okay. That's a very technical question. Maybe you can come up with a model of what you're describing. I should tell you the model I'm working with is very simple. I don't have a population. I just have one organism at a time.
Okay.
And the way I get creativity to be open-ended in biology is my computer program is a mathematician, and how do you say, their goal in life is to do well on a mathematical problem called the busy beaver problem. And that's a problem which has no algorithmic solution. So I picked, to challenge my organisms and force them to keep evolving forever, I pick a mathematical problem for which there is no general method. Right. You know, it's sort of an instance of either, Turing uncomputability or Gödel incompleteness. So that that way there will be no organism that achieves the best possible answer, and it'll have to keep evolving forever. So what I'm sort of doing is I'm taking Gödel incompleteness and transforming it into open-ended evolution. by considering organisms which are sort of mathematicians that are trying to solve a very difficult mathematical problem for which there is no general method. Okay? So that's sort of the game I'm playing. That's maybe relevant to your question, okay? So
so that's a really interesting way. Maybe we should talk about.
Are you at NUS? Are you in the quantum technology group there?
So I'm here at the Complexity Institute and at the Quantum Technology group. So there should be plenty.
Yeah, I'm giving a talk on Thursday at the Quantum Technology people
Right.
with the same title, but I thought maybe I would give a more technical talk there. So maybe we can explore these issues there.
Sounds good.
Okay.
Any more last question? Oh.
Hello. Yeah, sorry. This is a general question about information theory, I guess. I think you mentioned, I don't know if this is your view or Leibniz's, but that everything could be represented by zeros and ones. Was it a claim?
Well, yeah, Leibniz said the whole universe can be built out of zeros and ones. It sounded very theological. It's also, what is it called in French? What is it called? Numérique, I don't know. This is all digital technology. This is how our current technology works, right? Video is a string of bits, music is a string of bits, photographs are a string of bits.
Right.
So,
I'm trying to understand it. Do you mean to say everything can be built out of this? So sure, a lot of things can be, right?
algorithms can be built out of it. Oh, do you mean souls?
No, nothing like that. Sure, that too, right? But like bodies and computers, right?
Yeah, well, this is sort of an ontology, where everything is information. Everything is strings of zeros and ones.
Okay, so he thought this and you think this.
I'm sorry?
Leibniz thought this and you think that everything is information.
Well, I don't know. Maybe you want physical objects. This would be building a world out of information.
Okay.
Another idea is to say that material objects, the normal view is that the physical universe with energy and matter is the fundamental thing, and information is something built on top of it, an epiphenomena built on top of that. Another possible, that's the materialist view. It has a long history in philosophy. Then there's a thing called idealism. So in that view, information would be the primary thing, and so information and computation would be the primary substance, your ontology, and matter and energy would be an epiphenomena built on top of it. So that's sort of digital philosophy or digital physics, to the extent that you can develop it. I'm not saying the world is this way. It's a possible world, right? I don't know whether our world works this way or not. But I think it's interesting to see how far you can go with this view. And certainly Leibniz got enthusiastic about it enough to want to cast a silver medallion about it, which I think meant that he thought it was really a neat idea, but he couldn't convince the Duke of Hanover.
Okay, so I think we end just in time. So thanks to the audience for asking very interesting questions. I would now like to present a token of appreciation to Professor Chaitin. So please come.
Oh, should I get on the... Thank you very much. Yes. Thank you very much. Very beautiful.